am going to start with the next topic, that is topic 5, constraints handling in GA. Now, GA actually we use to solve the different types of optimization problems. Now, in most of the real world problems, actually we will have to handle some sort of constraint optimization problem. That means, there will be some functional constraints as well as objective function and the side constraints or the geometric constraints. Now, let us take one example of a constraint optimization problem. Now, supposing that I have got a function y equals to f x and this I will have to optimize, say either maximize or minimize. Now, subject to some functional constraints like g I x is less than equals to 0, where I varies from 1 to up to n. So, this is one functional constraint and this is the inequality constraint. Next is we have got h j x equals to 0, j varies from 1 to up to p. Now, this is actually one equality constraint. So, these are nothing but the functional constraints. So, these are the functional constraints, and here, so this is the objective function, and we have got the variable bounds that x is lying between x minimum and x maximum. So, this is nothing but the side constraint or the geometric constraint, and capital X is nothing but is a collection of all small x values like x 1, x 2 up to x m. So, this is actually the constraint optimization problem. Now, let me discuss how to tackle, how to handle so this type of constraint optimization problem. Now, here we have got small n number of inequality constraint and small p number of equality constraint. So, the total number of constraint is n plus p, that is equals to q, and the functional constraints, these are represented as phi k x, k varies from 1 to up to q. So, this phi k x is nothing but the collection of all functional constraints. Now, to handle this constraint optimization problem, we take the help of an approach which is called the penalty function approach. Now, let us see how to use this to tackle this type of constraint optimization problem. Now, supposing that I have got one objective function that is small f I x, and the variables are such that the functional constraint or some of the functional constraint are going to be violated. So, if there is any such violation of the functional constraint, so I will have to penalize, so that particular the solution by the penalty term, that is nothing but p I. So, I am just going to concentrate on the ith solution or the ith GA string, and corresponding to the ith solution, the fitness value is say f I x and the penalty is p I, and here I am putting so plus minus, the reason I am going to tell you, and the modified fitness is nothing but capital F I x is nothing but small f I x plus minus p I, and p I indicates the penalty. Now, this particular p I is having positive value, and supposing that I am solving one maximization problem. Now, for solving the maximization problem, so this penalty term has to be subtracted. On the other hand, if I want to solve one minimization problem, so I will have to add this particular the penalty term. Moreover, if a particular functional constraint is not going to be violated, or if it satisfies a particular functional constraint, for that the penalty term should be equal to 0. So, if there is any violation of the functional constraint, I will have to add or subtract the penalty depending on whether it is a maximization or minimization problem, and if there is no such violation of the functional constraint. So, we will have to put this particular penalty term equal to 0. Now, let us see how to calculate. So, this particular the penalty term. Now, here I am just going to write down one expression to calculate the penalty, that is P I, that is the penalty for the ith string by ith solution is nothing but C multiplied by summation k equals to 1 to q phi I k x square. Now, here, so this particular C is actually a constant, and the numerical value for this constant has to be decided by the user, and small q indicates the total number of functional constraints, and here the phi I k x. So, this phi I k x actually it indicates how much is the violation of this particular the functional constraint. So, what I do is we are going to find out the left hand side value and the right hand side value for a particular functional constraint, and by subtracting we try to find out how much is this particular the violation. Now, this particular phi I k x, it could be either positive or negative, and that is why to make it positive we use this particular the square term, and sometimes we also use the mod value to get this particular positive value in place of this particular the square term. Now, let us see how to calculate, how to find out this particular penalty value using different approaches. So, I am going to discuss a few approaches like how to calculate this particular the Pi value. Now, here actually what we do is we are going to use the concept of the static penalty first. Now, here in static penalty what we do, we try to use this particular expression to find out what should be the modified fitness. So, corresponding to ith solution, the modified fitness capital F I x is nothing but small f I x plus summation k equals to 1 to q C k r, that is the constant term, multiplied by phi I k x square. Now, here actually the C k r is the rth level violation of kth constant. Now, this particular numerical value we will have to define, we will have to supply before we start with the calculation of this particular the modified fitness, that is capital F I x. Now, how to assign this particular value, that is C k r, that I am going to discuss. Now, to discuss this, let me take one very practical example. Now, this particular example is as follows. Now, supposing that I am going to design shaft for a particular fan, say I am considering two fans, one is the ceiling fan, another is the table fan sort of thing. Now, supposing that the blades of this particular fan will be supported by a shaft. Now, I am just going to design the shaft for the ceiling fan, and I am also going to design the shaft for the table fan. Now, while designing this, we will have to consider one fact, that if there is any failure in the shaft of the ceiling fan, there could be fatal accident, the person who is sitting below may die. On the other hand, if there is any failure on the shaft of this table fan, there could be an accident, but it may not be so much dangerous. So, the person who is sitting in front of the fan may get hurt, but he or she may not die. Now, if I want to design these two shafts for two different fans, so I will have to consider two different values for this particular the C k r. Now, this is the way, depending on the practical situations or the requirement, the user will have to select what should be the suitable value for this particular the CKR. That means, supposing that I have got two functional constraints, out of these two functional constraints we will have to find out which one is more important, whose violation cannot be tolerated so easily, and if this is the situation. So, if one is more important, another is less important, we can assign two different numerical values for this particular CKR. So, once you have selected the numerical values for this particular CKR, now very easily you can find out what should be this particular the amount. That means, you can find out this particular the numerical value, and I can also calculate what should be this particular the modified fitness. Now, after some time I am just going to discuss one numerical example just to show you how to calculate this penalty term numerically. Now, then comes the concept of the dynamic penalty. Now, here actually what you do is, so this penalty term, that means this particular term is going to vary with the number of iterations. Now, let us see how does it work. So, capital Fix is the modified fitness, that is nothing but small Fix is the original fitness plus Ct raised to the power alpha multiplied by summation k equals to 1 to q mod value phi I k x raised to the power beta. Now, here I consider the mod value just to consider the positive value for this particular the deviation, and this c is actually a constant, user defined constant, alpha is another constant, beta is another constant, and t indicates the number of iteration. Now, here as t increases, what will happen to this particular penalty term? The penalty term is going to increase. The numerical value of this penalty term is going to increase. It means that at the beginning we put less amount of this penalty if there is a violation, but with the number of iterations the amount of penalty which we are going to put, that is increased. That means, initially we may allow a few infeasible solutions, but with time, with iteration, we should be more strict and we will have to put more penalty for the infeasible solution. So, that in ultimately we should not get any infeasible solution in the population of the GA. Now, once again I will be solving a numerical example to show the importance of this particular the penalty calculation. Now, here I put one note. So, this dynamic penalty is found to perform better than the static penalty as usual. Now, then comes the concept of this adaptive penalty. Now, here actually what we do is we calculate the modified fitness capital Fix, that is nothing but small Fix plus summation k equals to 1 to q, then comes lambda k t multiplied by phi I k x square. So, this is nothing but the amount of violation square of that, and this lambda k t we will have to define. So, using these conditions. Now, let us see how to define this particular lambda k t. So, t is nothing but the number of iterations. So, lambda t plus 1, that means the value of lambda in the next iteration is nothing but 1 divided by beta 1 multiplied by lambda t for feasible solution. That means, if there is no violation of the functional constraint. So, this is the expression which I will have to use, and if there is a violation, that means for infeasible solution. So, I will have to use lambda t plus 1 is nothing but beta 2 multiplied by lambda t, where this beta 1 beta 2, where this beta 1 beta 2 are greater than 1 and beta 1 is not equals to beta 2. Now, here I just want to mention one thing. According to this adaptive penalty, supposing that a particular functional constraint is going to be violated. Now, for this particular infeasible solution, we put high penalty value, and even if for feasible solution, when there is no such violation of the functional constraint, we put a small penalty value instead of putting 2 equal to 0. So, in place of feasible solution, so actually instead of putting penalty equals to 0, we put some small value. So, this method is slightly different from the dynamic penalty approach and static penalty approach. Now, I am just going to concentrate on a numerical example just to explain the method of this particular the penalty function approach. Now, I am just going to consider a constraint optimization problem of two variables x 1 and x 2. Now, the objective function is as follows: minimize f of x 1 comma x 2 is nothing but x 1 plus x 2 minus 2 x 1 square minus x 2 square plus x 1 x 2. So, this is the objective function subject to x 1 plus x 2 less than 9.5 and x 1 square plus x 2 square minus x 1 x 2 is greater than 15.0 and x 1 x 2 are lying between 0 and 5. So, this is the objective function, these two are the functional constraint, and this is nothing but the side constraint or the variable bounds. Now, let us see how to calculate the penalty terms using the concept of static penalty approach, then comes dynamic penalty approach and adaptive penalty approach. Now, let me consider one set of values of the variables like x 1 equals to 2.0 and x 2 equals to 3.0. Now, what I do is in static penalty, so here actually we have got two functional constraints. So, q is equals to 2 and the static penalty which is denoted by Ps is nothing but summation k equals to 1 to q c k phi k x square. Now, let me assume that C 1 equals to C 2 equals to 10. Here the first functional constraint is not violated. Now, let us check the first functional constraint. The first functional constraint, that is nothing but x 1 plus x 2 is less than 9.5. So, here if I calculate the value for this particular left hand side corresponding to the first functional constraint, that is left hand side is nothing but x 1 plus x 2, that is 2 plus 3 5, and the right hand side that is your 9.5, and 9.5 is greater than 5.0. So, there is no violation of this particular the functional constraint. And as I mentioned that if there is no such violation of the functional constraint, so we put the penalty term equals to 0. But for the second functional constraint there is a violation. Just to check that, once again let me concentrate on the second functional constraint, that is the left hand side, for the second functional constraint is nothing but x 1 square, that is 4 plus x 2 square, that is 9 minus 6. So, this is nothing but 13 minus 6, that is 7, and the right hand side is equal to 15, and 7 cannot be greater than 15. So, it is going to violate the second constraint, second functional constraint. Now, for this particular violation, actually what we will have to do is, so we will have to find out how much will be the penalty value. Now, penalty value for this particular, the second functional constraint is something like this. Here we can find out the deviation, that is 7 minus 15 is the deviation, because left hand side was 7, right hand side was 15. So, deviation is minus 8. So, I can find out the amount of static penalty, that is equals to 0 for the first functional constraint, because there is no violation there, and for the second functional constraint this is 10 multiplied by minus 8 square, and we will be getting 640. Now, so this is actually the amount of the static penalty. So, this is the way actually we will have to calculate how much will be the penalty value using the concept of the static penalty approach. Now, I am going to discuss the concept of the dynamic penalty. The dynamic penalty is calculated as follows, like P d is nothing but C multiplied by T raised to the power alpha summation k equals to 1 to 2 mod value phi k x raised to the power beta. Now, let me assume that T equals to 1, that is the next generation, alpha equals to 2, beta equals to 3. Now, using this actually we can find out what should be the penalty term for the second functional constraint, and for the first functional constraint there is no violation. So, the penalty term will become equal to 0. So, we take C equals to 10, and now I am just going to put the numerical values for all these symbols. Now, if I put the numerical value like C is equals to 10 I am putting, and T equals to 1, alpha is equals to 2, beta is equals to 3, and the amount of violation also I know, that is minus 8. So, if I put all such numerical values, so I will be able to find out what should be the value for this dynamic penalty, and which is coming to be equal to 51,200. So, this is the amount of the dynamic penalty. Now, let us see how to calculate the adaptive penalty for the same constraint optimization problem. Now, we take beta 1 equals to 2, beta 2 equals to 3, and let me consider that lambda t is equals to 10. And using this particular expression, so we will have to calculate this, the amount of adaptive penalty, that is P A is nothing but summation k equals to 1 to 2 lambda k t multiplied by phi k x square. Now, here as I told that if there is violation, definitely I will have to find out the penalty term, but whenever there is no such violation, then also I will have to calculate, so this particular the penalty term. And according to this particular formula, like lambda t plus 1 is nothing but 1 by beta 1 into lambda t for the first functional constraint, because here there is no violation of the constraint, and I will have to use for the second functional constraint. So, this particular expression, that is beta 2 multiplied by lambda t, because here there is a violation of functional constraint. Now, if I put the numerical values for the first functional constraint, so I will be getting half multiplied by 10. Now, from where I am getting half, so beta 1 equals to 2, so 1 divided by 2 multiplied by 10, and here for the second functional constraint, so this is 3 multiplied by 10, so 30. Now, using this I can find out what should be the penalty term, but before that I will have to find out the amount of violation. Now, if I just compare the left hand side and the right hand side, for the first functional constraint, although there is no violation of the functional constraint, the difference between the left hand side and the right hand side is found to be minus 4.5, and for the second functional constraint, the difference between the left hand side and the right hand side is minus 8.0. Now, using this concept of adaptive penalty, I can find out that is 5, that is this lambda multiplied by minus 4.5 square plus 30 is this particular lambda into minus 8 square, and if you calculate, so for the first functional constraint, so I will be getting the penalty term something like this, and for the second functional constraint I will be getting this is the penalty term. Now, if I compare these two penalty term, so for the functional constraint where there is violation, the amount of penalty will be higher compared to the other where there is no violation. Now, if I just add them up, I will be getting the amount of total penalty like this. So, this is the way actually we will have to calculate the penalty term. Now, once you have got this particular the penalty term, so I will have to calculate the modified fitness, and based on the modified fitness, now I will have to carry out the reproduction scheme or the selection scheme in genetic algorithm. So, that depending on the modified fitness, the reproduction scheme selects good solutions for the mating pool. We have discussed the working principle of a binary coded GA, and now I am just going to concentrate on the merits and demerits of genetic algorithm. Now, one good advantage of this particular genetic algorithm is it is a robust optimization tool. It can solve a variety of optimization problems. Now, here the chance of the GA solution for being trapped into the local minima is less, because this is a population based approach. We start with a number of solutions selected at random, and moreover actually what we do here, we use the operator like mutation, which also helps us just to come out of the local minima problem. So, here in GA there is a chance that we will be getting the globally optimal solution. Now, genetic algorithm can handle the integer programming problems and mixed integer programming problems. That means, when the variables could be of integer and real, and sometimes we will find that there could be a good combination of the real and integer variables. Now, for handling that type of optimization problem, so GA is found to be very efficient. Now, for the discontinuous objective function, GA can perform optimization because GA does not require the gradient information of the objective function. And as I have already mentioned that we face a difficulty with the traditional tools for optimization for their parallel implementation. Now, as GA starts with a population of solution, there is a possibility we can implement genetic algorithm in the parallel platform. The whole population is divided into say either 3 or say more than 3 groups, and those are assigned to 3 or more than 3 CPUs, and there will be computation and there will be the message passing instruction codes running there, and it helps just to do the interaction between the 2 PCs or among so more than 2 PCs just to collect the information, and consequently the effective computation time to solve a complex optimization problem will be reduced. And GA has got the advantage here, we can do this parallel implementation very easily, because this is a population based search and optimization tool. And as I told that this is very robust, GA is very robust and it can solve a variety of problems. However, so this particular GA has got a few demerits. Now, GA is computationally expansive and consequently, there will be slow convergence rate. Now, here we are going to face one problem. Supposing that we want to carry out some sort of optimization online, but this GA is going to take a long time to give that particular optimal solution. So, there is a problem, we cannot implement or we cannot use this particular GA for online optimization. And GA is actually a black box optimization. Now, let us try to recapitulate the way we run GA to solve a particular problem. So, once we have got a problem, once the mathematical formulation of the problem is with us, we know what is the objective function, what are the functional constraints, what are the variable bounds, and accordingly what we do is in the code of GA, we write down the expression of the objective function, we set the range for the variables and we select the GA parameters like what should be the population size, what should be the probability of crossover, what should be the probability of mutation and so on. And once we have selected the GA parameters, now we allow the GA to run. The GA will run for a large number of iterations and ultimately you will be getting that particular optimal solution. And truly speaking, we do not know what is happening inside the GA, but if I wait for a few minutes or few hours, ultimately you will be getting that optimal solution. That means, GA works like a black box, the user actually does not know what is happening inside the GA. But here I just want to put one comment. Nowadays actually we generally do not consider GA as a black box optimization. Now, I will be discussing in details after some time and I will show you that we can also investigate what is happening inside the GA during this particular optimization, that I will be discussing after some time. Now, here actually in GA there is no mathematical convergence proof and that is why many people actually do not believe GA, but there are some indirect proof like the proof using the schema theorem which I have already discussed, or with the help of some hand calculation I have shown that GA can improve the solution and it can find out the optimal solution. So, these are all indirect proof that GA can find out the optimal solution, but till now unfortunately there is no concrete mathematical convergence proof for this particular the genetic algorithm. And another thing I just want to put, which is very important, the user should know the grammar of GA, and unless he or she knows the grammar, so he or she will not be able to set the GA parameters properly, and if the parameters are not set properly, there is no guarantee the GA will be able to hit the globally optimal solution. So, these are all disadvantages or the demerits of the genetic algorithm. Now, actually comes the concept of efficient optimization tool. Now, supposing that we have got a very complex real world optimization problem and we will have to solve that. Now, to solve that, if I take the help of a genetic algorithm is a very powerful tool for global optimization, but its local search capability is not so good. So, if I use GA to solve that particular problem, so it will carry out a huge search, but it may take long time to hit the globally optimal solution. So, what we do is we first use GA to carry out the global search and we try to find out a region, that is the region of interest, where there could be a possibility that the globally optimal solution is going to lie. So, what we do is we take the help of another very good local search technique, for example, say steepest descent method. Now, once we have got some good region with the help of a GA, we try to carry out further search with the help of a steepest descent method, which is a very efficient local search method. So, to solve this complex optimization problem, actually we consider both the things together. Say one tool for global search, that is genetic algorithm, and another tool for efficient local search, that is the steepest descent algorithm, that is a gradient based algorithm. And combining these two algorithms, we can develop a more efficient optimization tool. And we have seen to solve a variety of difficult real world optimization problem. So, we will have to go for this type of efficient optimization tool. Thank you.